and welcome. Today we'll start the chapter Rotational Mechanics. Now, this is considered as one of the most difficult topics in physics. But if you pay enough attention to the basics, you would find that it's not as difficult, but instead this is one of the most interesting topics in physics. And this chapter involves all that we have learned so far in mechanics. Right. So before we start our discussion on rotational mechanics, let's first understand what a rigid body is. So a rigid body is, as you understand, is a body which does not essentially change its shape, right? So in strict definition, rigid body is a body where the distance between any 2 points on the body would not change. So a rigid body is such that distance between any 2 points on the body do not change. That does not change. The distance does not change. So this means that a rigid body would be a body where the distance between any 2 points would not change. Take a simple example. Think of a box. Now, if you move this box, the distance between any 2 points would not change. But instead, if we have 2 boxes combined through a spring, then during their movement, you can see that the distance might change, right? So this arrangement is not a rigid body, but the previous example where we had a single box, this is the case of a perfect rigid body, right? So in a rigid body, since the distance would not change, let's see what the consequences of this assumption would be. So what I've drawn here is a perfectly rigid body. Now, I'll assume that this line that I've drawn is the line around which this body is rotating. Right. So now, first of all, to simplify our calculations, I'll assume that this rigid body is made up of a lot of smaller bodies. Right. Now, we have dealt with such situations before. If you want to take such a case, you have to take an infinitesimally small particle and then integrate over the entire body. But right now, I'm just viewing this body as a collection of bodies which have finite mass. Right. So if I do so, and I've given you that this body, say, rotates with an angular speed omega. I hope you remember angular speed and angular velocity. We read about this in circular motion. So it is given that this rigid body is spinning about this axis with an angular velocity omega. We wish to find the kinetic energy of this body. So, given is the situation that there is a rigid body of mass m spinning about an axis with a constant angular speed omega, and we wish to write the angular speed, the kinetic energy. So, the kinetic energy, we know that if we take any one body, like say this, let me call it Mi. So this is of this collection, this is one particle and I'm giving it a general index Mi. So I can assume that this body is made up of, say, n masses, M1, M2 till Mn, right? So I'm considering a general body and I'm giving it the index I. So the kinetic energy of this ith body, I know by definition, would be half into the mass, which is Mi, into its speed square. Let's call it speed Vi, and then this gives us the expression for kinetic energy for this single body, right? Right. So the total kinetic energy logically would be the sum of kinetic energy of all these bodies, right? So if this single rigid body is made up of 10 smaller bodies, then if you find kinetic energy of all of these 10 bodies and add them up, then you get the total kinetic energy for this rigid body, right? So same is the case here. The total kinetic energy would be the summation of all these kinetic energies, where this index varies from I to 1 to n, right? If you have n such bodies, right? So now it is given to you that this body is spinning with an angular velocity omega, right? So let me say that the perpendicular distance of this ith body from this axis about which it is spinning is Ri, right? So Ri is the distance from this axis of this ith particle of which we are assuming the body is made, right? So if Ri is the distance, I hope you can imagine this body would go in a circle of radius Ri. Look at this animation to understand this better. You see the axis of rotation, the entire body. Now, if I give it a spin, you can see that this point traces out a circle, and the radius of the circle is nothing but its distance from this axis, right? So now, since a circle is being formed, recall that we know that linear speed in case of circular motion is equal to radius times the angular speed, right? We have read this before in circular motion. V is the tangential speed, omega is the angular speed, and r is the radius, right? So if we use such a relation, we can write that the translational speed, the tangential speed Vi is equal to the radius Ri into omega, right? So we can write this expression for this ith particle. So this equation can be written as summation of I from 1 to n half into mi into Ri square omega square, right? So now in this expression you see that omega is a constant, right? So we can take omega out of the summation and we could write something like half can also be taken out because it's once again a constant. So you would have a term like half into summation of mi Ri square into omega square, right? So the total kinetic energy of this body when it spins is of the form half into the summation of mi square into omega square, right? So now let's come to the entire idea which we want to establish here. We are going to compare this expression to the original expression of linear motion. Kinetic energy we know is equal to half into m into v square. So we see a similarity in these two expressions, right? Because in this case you have an expression of half into a term into the square of angular speed, right? And in the linear case we have half into mass into the square of linear speed. So this half sees its analog, omega clearly sees its analog. This is linear speed, this is angular speed. So we could say that these two terms are also sort of an analog of each other.